Hello everyone, very excited to see you all here. Um, this is Murali Talluri. I'm a specialist solutions architect at Databricks. I've been with Databricks for a couple of years now.
Good morning, everyone. This is Dattatraya Walake. I'm a specialist solution architect in data engineering and a couple of years with the Databricks.
Today we are going to walk you through advanced JSON schema handling and demuxing. By the end of this talk, we hope you'll have a good understanding on how to ingest and process JSON data with varying schema and how demuxing can be simplified and can be done at scale using DLT. So by the end of this talk, right, um, we'll talk about JSON schema handling and we'll understand why JSON schema handling is even important, right? Modern data pipelines have to deal with, semi-structured data like JSON, and this data comes from variety of sources like IoT devices or your application logs, or APIs, right? And we don't know the schema of this data that we need to process, and the schema of this data changes often, and we often have no control over the upstream that ingests this data. And everyone loves to ingest JSON data because it is flexible by design, and our data pipelines have to be flexible in handling it too. At least that's the expectation. Now let's see how JSON data is usually processed. Is using from JSON. From JSON is a function in Spark that parses a JSON column given you specify the schema. This is how the schema from JSON looks like. It returns a struct and you basically have to extract fields from that struct, right? The major challenge with using from JSON is it doesn't support schema inference and evaluation, meaning you have to specify the schema as a parameter at the beginning, right? And let's say you specify the schema, and over a period of time, if the data has new fields or the schema changes, those changes would be ignored because the schema doesn't have those fields, right? So that's a challenge. Now let's look at some examples of how from JSON is typically used. We'll quickly go over this, right? So the first is RDD way that most of you might know. What you do is you pick a record from the batch of data and convert it to an RDD and then convert it to a data frame and get the schema of it and pass it to from JSON. This is how the code looks like. And the second way is like, this is lightweight comparatively. What you do is you again pick a batch from the batch of records, you again pick a single record, get the convert it to a data frame and then use schema of JSON on top of that and get the schema and then pass it to from JSON as a parameter. The code looks like this. In both these approaches, that you might end up picking that random record from the batch of data that might not have all the fields, right? So again, you're missing fields. The third approach is basically to use map string comma string as a schema to from JSON, and then you basically explore of that map, and then you group by all the fields and pivot and act by the key value pair, right? When you do this, it's effective in a way like you capture all the fields in your JSON data, but this is a very memory intensive operation, and and when you do this, all your fields are passed as strings because that's a hint that you specified, right? That's not what you want. Even the digs and arrays are going to be like strings, and you have to do further processing on it. Now let's see how we can use variant to handle JSON processing with varying schema. What is variant? Like most of you might know, variant is a data type in Databricks that uses binary encoding format under the hood to effectively store and query JSON data. When you use variant, you don't have to worry about the schema in front, like specifying schema and how the schema evolves and all that. You basically ingest it as variant. Using variant, it's very easy to land data into your bronze layer like Databricks. The reason is when you read JSON data as variant, your ingestion always succeeds as long as your JSON data has valid fields, right? Or as long as a valid JSON record. And variant is actually a very good candidate when the schema of your data changes very often. And often you can't specify the schema. Let's look at some examples here where variant is a very good candidate and maybe the only option. So I have a data provider who is ingesting data with the schema. And the first field here, type indicates like the provider ID, something like that. And the rest of the fields here, there are like 7 fields, I think, the outer fields. they are your actual data. And now I have another provider who is ingesting data with this schema, and I end up having 100 different providers who are ingesting data with 100 different schemas, right? Um, what you need to do here is that all the data is coming into a single storage location, and you have to basically pass the JSON data and then route it to the respective tables, right? So if you typically use autoloader, let's ignore the variant part for now. If you typically use autoloader and try to do regular JSON parsing, what would happen is autoloader would do some sampling based on the files or the size of the data, and then it gets the schema from that sample. It uses that schema, right, and try to read the entire data, and it realizes there are more fields in the data. So it's going to restart, merge the schema, and try to get all the fields from your data, and you might end up getting close to 700 fields because you have 7 fields in each no, type of schema, right? So, and you will end up getting in your bronze layer one delta table with 700 fields. That's 700 columns. That's not what you want, right? Now let's look at an variant code example how this can be done. You can actually use the same autoloader, but you can ingest JSON data as variant. This can be done by specifying that option, single variant column. And when you run this code, what will happen is you don't have to worry about the schema, parsing, sampling, and all that. What it would basically do is you get a delta table with just one column instead of 700 columns that you had before. One column, and the name of the column is data, and the type of it is variant. And this is going to be way faster for your ingestion on your bronze layer, because it just checks if your JSON data has valid records, right? As long as it's not a corrupted record or something, the ingestion succeeds. Now the goal is that now you have this data, it's a top one field, right? Now how do you go about extracting those 100 schemas from it and route them to the respective tables in Silver, right? This can be done using schema of variant ag. What schema of variant ag would do is it's going to give you the combined schema from all the fields. It's going to handle things like type merging, like let's say you have a field that's string and also integer, or maybe integer and also long, right? It's going to do the type merging and combine them to long or string based on your fields, right? And it's going to do all that out of the box for you. And you can look at this code. What we are trying to do is we are extracting the type field basically, and then trying to get the schema of that field, a schema for that data provider type, and then applying that schema back on your bronze layer and parsing the JSON and routing it to the respective Silver table. Now in this example, we just have, it's a simplified example, to be honest. So where we have just 100 providers, we have seen cases where we might have 1,000 different providers or more, and the schema for each provider would vary, right? Within each provider, we just have 7 fields here, but you might have more fields there, or any level nested, right? Still, using the same technique, we can effectively handle ingestion using variant. Now, your scenario might be different, right? Where variant is schema on read. Your scenario might be that you don't have 100 different providers, you might have very few providers, and the schema of the data changes over a period of time, maybe it changes daily also, right? And your goal is that you don't want to use variant because the schema already, you want to enforce the schema on the data in your bronze layer itself maybe, and you want to do it without having to specify the schema because you don't know the schema in the first place, and you don't want to worry about the new fields getting added. You want your pipeline to be robust enough to, like the flexibility, right? That's what we talked initially, like how JSON is flexible. You want your pipeline to be flexible enough to handle all this. How do you do it? This can be done using same from JSON that we discussed before, but in DLT you can do it by specifying schema as null. What you do here is that when you specify schema as null, it's going to kick off the automatic schema inference and evaluation for you. Here is how the syntax of from JSON looks like. You can see that schema is null, and we have to specify the schema location though. Schema location is where you're telling it to store the schema of the inferred or the inferred schema of your JSON data, right? And it is managed by DLT, meaning if pipeline is deleted, so it's going to be deleted, but it is managed by DLT environment. So Let's see how this is done out of the box for you, right? Let's get into some details. What happens when you run the pipeline with from JSON specifying schema as none is, with the very first run, it's going to see whether there is any schema in that schema location you specified, right? There is none. So what it would do is it would do a schema of JSON ACK to get the scheme of you know, all the data that you have that it needs to process in that batch. If the streaming engine decided to do these many records in your batch, it's going to get the schema of JSON ACK and get the all the fields, and it's going to write it to that location, and it restarts the pipeline. And now in the restart, after the restart, it's going to read your data with that schema. That's how it does the first step of automatic schema inference, right? Uh, Now, after doing few batches of data, it realizes there is a schema change, right? Then what will happen is, um, it's going to infer those new fields that you added, and it merges the schema to that schema location, and reset the pipeline again, and tries to read the data with that schema. So that way, it is also evolving in that schema. Your schema of the data as it evolves, it is stored and evolved, and it's going to be processed with that schema. Okay, so what happens today with with this functionality is that, let's say you are running this pipeline, and it decided to process maybe 1,000,000 records in a batch of data, for example, and your batch has 3 schema changes at the beginning, and the middle, at the end. When it sees a record that has new schema, what it does is basically it's going to infer the schema and merge the schema and restart. Now it needs to process the same 1,000,000 again, right? With that schema, it sees another schema change. It's going to restart again. So what happens today is that if you have a batch of data that has 3 schema changes, meaning 3 new fields are there, it is restarting 3 times, right? When DLT gets to DBR 16.4, that's actually it's coming next week. When it reaches that point, we have this improved schema evolution by batch, meaning when it sees a new field, it's not going to just infer off of that new field and then restart the pipeline. It's going to do the schema of JSON ACK again on the entire data to capture all the new fields you have in that batch and merges, so that even for 100 schema changes in your batch, right, it's going to restart only once. So this is effectively coming maybe next week when DBR 6.4 is going to be available in the current channel or preview, right? It's already in preview, I think. It's in so you can start using that. This is going to save a lot of time in terms of restarts too. You can also override schema inference, by specifying schema hints, right? The expectation is that for those fields you give the hint, they'll be honored by from JSON, and the rest of the fields you are telling, automatically infer and evolve. Let's look at an example here. I'll quickly go to the example. I have this JSON data with this schema, right? And I'm ingesting 25,000,000 records thus. And after over a period of time, I want to introduce another field that's in field 2, and I'm inserting it as long, and I have 25,000,000 records here. And then we're changing the type of int field, and now we are inserting strings for that field, right? And and we are also introducing another field under the dict field, nested field, right? For it, a new field doesn't have to be an outer field. Any level nested field is going to be considered as a new field, right? And now I have 25,000,000 records, and then I'm inserting another field here, nested field 3. That's highlighted in the highlighted there, right? So what happens is you have now 100,000,000 records, right? And there is one original schema, and you have 3 schema changes, and there is one type change, but 3 new fields are there, right? Now let's see how from JSON and DLT would handle this for you, right? The highlighted code tells you how you can call from JSON to use automatic schema inference and evolution. And I have million records here, right? I have like 100,000,000 records here. I'm specifying max offsets per trigger as 10,000,000. This is 10,000,000, meaning I'm telling the streaming engine to do it in 10 badges, right? When you run this code after processing 100,000,000, right? So this is how the schema of your delta table looks like, and you can see all these new fields got added. What happens on the DLT side is that the first restart is going to be obvious, right? You can see it restarted 4 times. The first restart is because there is nothing to infer, so it's going to do schema of JSON ACK and infer, and then merge, and then try to process. The first, you can't avoid the first restart, and there are 3 restarts because because of the 3 schema changes. It sees a new field, it's restarting, and then merging schema, and then processing again. One important thing to notice here is that because we inserted int field 2, as basically as an integer. That's what we declared, or long what we declared. And later we're inserting strings there. For those records, infill2 is captured as rescue data column, right? Now, how do we avoid so many restarts? And how do we make sure there are certain fields that you want to do? You wouldn't want to worry about the rescue data column, right? In your logic to process those fields. So how do you work around that? For that, we have the technique called schema priming. What schema priming is basically preloading the schema of your data before you actually process the data, right? So how this can be done is using schema of JSON hack. The same technique that from JSON uses under the hood, right? So what you do is you basically do a schema of JSON hack and store the schema, and then you pass it to as a schema into from JSON. That way you're priming, right? The advantages of priming is basically you can control the schema entrance and evolution, although it's handled automatically. If you want to say, like, like in the previous example where infill2 originally came as a long or an integer, and now the type changes, right? So because it's already persisted, it's going to go as rescue data column. So you want to have some sort of control over the inference and evolution by priming the schema, and so that you don't want to worry about the rescue data fields. And you can also avoid multiple restarts of your DLT pipeline, basically. And schema priming also help you to stabilize the downstream pipelines because you know the schema of the data that you're processing, right? Now let's look at quickly look at a demo for like how from JSON can be used, right? I have this pipeline here. This is the code for the pipeline where I'm using max offsets. I'm specifying schema as none here, right? And when you look at this pipeline, what you can see is that uh, it restarted these many times. If you look at the example here, you can see the first time it didn't process anything, right? Because there is no schema at all in the schema location. It did a schema of JSON hack, and it tries to read few batches because your batch size is 10 million, right? It read 2 batches. That's why it processed 20 million and did it, and then saw a schema change and restarted. You can see here in this example, it figured out that there is a new field, right? Here in the schema location, encountered a new field during parsing, right? Yeah, there you go, in field 2. So it saw that and it restarted, and that's why it restarted so many times, right? And then eventually it processed all your 100 million records. Now let's look at an example how you can prime your schema. By the way, in the previous example, it took like almost 17 minutes or 18 minutes roughly, right, to process your data. Now you can prime using, now what I'm doing is from the same topic, I'm trying to prime using schema of JSON hack, and I'm storing it as a YAML file to volume, right? And what I'm doing in my DLT pipeline is basically I'm reading that prime schema and passing it as a schema hint here. Now when you do that, what happens is the pipeline processed all those 100 million records, right? It didn't restart because you basically essentially what you're trying to do is you're telling it, hey, this is my schema and process it like this, and you didn't see any new fields in the data, so it never had to restart. Now over a period of time, if you see new fields or you expect like more fields to are going to be coming and you don't want restarts, you can use the same technique of priming again and passing it as a hint. And this priming technique can be essentially useful. Let's say you want to process maybe 10 billion records, and you don't want to read all that right away, right? So and maybe your batch size is 100 million, meaning it has to go in like so many batches, and you pretty much know that the schema is changing and you want to avoid the restarts. In this case, it restarted 4 times, but you might end up having like 100 schema changes too, right? Because it's JSON. So you can use a technique to effectively control and also make sure few fields they don't go to rescue data column. Quickly walk you through here. In this case, out of the 100 million records, we can see 14 million records went to rescue data column for that in field 3, right? In field 2, sorry. And if you use the technique, so nothing went because you pretty much know what to what to expect. You told it like pass it as a string and all that. So yeah, this is how you can use it. And with this, I conclude the demo, and I want to pass it to Datta for the next session, event demuxing.
Thanks, Murali. So yeah, so what is event demuxing? So event demuxing is the process where we can actually separate, route, and classify the events based on the certain criteria, right? Like this, for example, topic or the content of the payload. like event type. And this process is essential in the big data analytics since these events are generated by diverse systems with the mixed formats because the modern system supports these even modern system supports different types of these serialization formats like JSON, protobuf, to and etc. So to parse this mixed data using a single system will be challenging, and where this event demuxing will help to design these essential targeted events, and based on that targeted events we can focus on specific streams and get the insights in the time. And also this event demuxing process helps to design the scalable and easily maintainable systems. So that's why the event demuxing is important. So this is the technique. Uh, so generally, we do the event demuxing two ways. One is a topic-based eventing, where the producer or the events are published to the dedicated topic. And generally, this is useful when you are actually handling operational use cases, where the producer publish the events to predefined topics. So this is a one-to-one, and this demux by based on the topic. So this is not much flexible to demux. So use case like e-commerce where the order types events can publish to the order type topic, and payments can publish to the payment type topics. And the next type is the payload based multiplexing. This is super flexible because you can demux by anything. So instead of actually having independent topics, everything comes to the shared stream. So for example, in the ad tech use cases, you can actually publish all ad events to the shared streams and then demix by based on the event type. So for example, uh, click events or the view events or the different types of events, you can demux by them. So it is super flexible to demux. So Demux actually gives this tons of benefits to process the heavy event streams. However, like while implementing this event processing, it comes some challenges since these events are generated by diverse systems with multiple formats. We should have systems to capable to process or deserialize these different formats. Let's say if your system is not capable to support the backward compatibility, so with even a small schema changes, your system will fail, and that will have impact on the downstream systems. Also, for handling low latency, for example, these operational use cases. So, it is a tricky when you are handling low latency event streams with the your demux logic. And then with the scalability issue also, because the modern systems supports to generate the events. For example, it per second it may generate millions of events, so your system should capable to handle those events. Otherwise we can see the throughput gets squeezed. And also some special events like uh, whenever special events, like for example in the advertisements, when you are doing camping, then you may see unpredictable traffics. So if your system downstream system is not capable to handle, we may see the back pressure on the upstreams, and there is a possibility of losing some records too. So your system should be reliable, which whenever your pipelines are failed, it supports exactly one semantics or at least one semantics, and handling that in the distributed systems is not small speed, right? And then other issues like it should support the compliance and the security issues because events comes with some sensitive data sets too. So how we can handle all this? So using Sparks on Databricks and the DLT, this simplify this overall event demuxing pipeline. So the Databricks has a native functions to parse the different formats. Like let's say your data is coming, the binary payloads are coming in the protobuf formats or the Avro formats or the JSON formats. Databricks has inbuilt functions like from protobuf or from Avro. So we can easily parse those events without having additional setup or tooling. And also it supports because now many of the event systems supports to support schema registry to support the evolving schema. So we can seamlessly integrate the schema registry while using these functions in natively. So using that, we can get the data into the bronze. So as we know, like in the Databricks platform, we can design the medallion architecture to leverage the different layers. So here also we can leverage using medallion architectures. At bronze data, you can get data in any format, and these native functions can support to deserialize the data. And on silver layer, we can do actual demuxing. So the demuxing is method of like we can achieve through the fan out options. Like the fan out, like you can read the source, single source, and write to the multiple targets. So to do this fan out options, the DLT provides the flows and API, flows and sinks APIs, where using those flows and API, we can seamlessly implement these fan outs. And currently it supports the different sinks like Delta sinks, Kafka sinks, and the for each batch sync. If you are familiar with the structure streaming, you know the for each batch. So this is a similar semantics supported in the DLT. Um, so let's say the operational use cases, if you want to write the data to Kafka sync, so we can use the Kafka syncs here. And mostly where our customers we are seeing, they're demuxing their data to the Delta formats. So the managed Delta tables created using the flows. And let's say if you want to demux the data to external Delta format tables, there we can use the Delta syncs. And then Kafka syncs for the operational use cases. And the for each batch syncs helps like your demux comes with some complex logic. Let's say you want to enrich your event with the reference data sets, or like you want to apply some uh, rules before, like let's say you want to quarantine the bad data sets to Kafka, and then you want to write valid data sets to Delta. So in that case, we can use for each batch sync. Um, this API is designed in such a way, like for each sync, it creates their independent stream. So if you're not aware of the DLT is the declarative pipeline framework, which is built top of the Spark streaming. So it provides all the features out of the box, and many maintenance tasks is handled automatically. If you are aware, like for example, the checkpoint management, like when you are using structured streaming, you have to maintain checkpoint explicitly, but the with the DLT, those tasks handled automatically, and these events are processed incrementally. So because of that, like you can actually control specific demux. Let's say you are demuxing multiple streams, and some streams may require additional resources or additional complex logic. You can tune individual streams. So using this flows APIs, and also these are the declarative APIs. So we can seamlessly handle multiple syncs and API using this DLT declarative API. And also it supports the idempotent writes. And if you have any complex merge logic, then it also supports merge API. Using merge API, we can achieve those complex implementation. Um, Currently, it supports like we can run 25 streams concurrently, and this is a soft limit because this again depends on how heavy your uh, demux logic is, how and what is expected SLA throughput. Based on that, we can tune, but we recommend to run 25 streams to one pipeline. But however, we are seeing many of our customers are actually demuxing hundreds of streams, and doing this like manually, since we cannot run all 100 streams on the same pipeline, we have to create the multiple pipelines, right? And doing that manually, it's impractical. So DLT APIs, the pipeline API supports to create this pipeline dynamically and allocate these newly created or newly onboarded topics to new pipeline using some configurations. We'll see that those details in the demo, how we can actually do this auto allocation. Uh, this is a code snippet uh, where you can, let's say your payload types are in the Avro format. We can use just from Avro and integrate with the schema registry. And the from protobuf we can use, or without with schema registry or without schema registry also we can use using from protobuf. So these are the simple like methods, native functions. Without having additional setup, we can pass the data. So let's see this in action, how we can implement. Yeah. So as part of this demo, I'm considering the AdTech use case, and where I'm creating the 5 independent topics, and there is one fact topics where all event types are published, um, and the data we are creating in the JSON format. And I'm covering 4 use cases, like how we can implement topic-based event demuxing. The second use case is how we can do the payload-based demuxing, and for the low latency, how we can use the Kafka syncs, and how we can implement the complex use cases using for each batch sync. So this demo has set up through the 3 steps, and in the README you can follow README how to set up this demo, what are the prerequisites, and there are some private preview and disclaimers, like there are some features we are using in this demo are in the private preview feature, so they will be available as is, or if there are any changes, so you can follow that important notes. So in step 1, what we're doing, we are creating the sample topics and publishing the data to the sample topics. And also I'm creating here the schema sampling using schema of JSON as we just saw in the previous demo. So this will create a YAML configuration, and it will map the topic to schema, and also it captures some metadata. Um, Along with that, we are building a configuration system table, which will be used for the auto allocation. Like, uh, let's say if we have existing pipelines and the pipeline has a space to allocate newly created topic, then we can allocate this topic to existing pipeline, or we can create a new pipeline. So as part of this demo, I'm using a 5 topics per pipeline. We are using 5 topics, and if the new topics comes, then it will create the new pipeline. So let me run this. So it will create the total 6 topics. Uh, yeah. Yeah, and this, it will create this configuration, and this configuration table will look like this. So it is created the 6 topics, and we are limiting 5 topics per pipeline. So if you see here, the first 5 topics are assigned to the pipeline one, and the last topic it is assigned to the new pipeline. And we are capturing some metadata like the type and the event type. So basically, when you are processing the payload based event, you need that criteria, right? Like either the event type or any metadata from the payload. Um, yeah. And in the step 2, it will create the new pipeline and allocate the existing topics or newly created topic to existing pipeline, or if the existing pipeline doesn't have enough capacity, then it will allocate, it will create the new pipeline and do this. So this allocation will happen in round robin fashion, so that let's say you have a multiple pipelines are exist, and you are onboarding the new topics, then these new topics will be distributed evenly. Yeah. And then the last step, before that, I would like to show how this looks. So the use case 1, where we are actually demuxing based on the topic. So if you see here, it is created the five node. So here we are actually reading the data from the Kafka and demuxing to the delta sync. So for 5 topics, it creates the 5 syncs and 5 flows, and each stream has each flow has its own stream. So all these five streams are actually running independently. And the second use case we saw, here I'm actually using the fact topic. So this is all add event topics. Here I'm actually covering 3 use cases. Uh, One is like how to write this data to Kafka sync, and then how we can actually use the delta syncs, and the complex use case we are using the for each batch sync. Uh, and using this for each batch syncs, we are writing invalid records corresponding to Kafka topics, and valid records we are writing to the delta sync. So let's see how it looks in the delta pipeline code. So yeah, so DLT provides this declarative API. Using this DLT for each batch syncs, we can create a sync. So while creating syncs, you can provide the name, and if you see this for each batch semantic, it is similar like for each batch. If you are familiar in the structure streaming, it provides you the data frame and the batch ID, and then accordingly you can implement the demux specific logic inside this. So here where we are writing the valid records to the delta sync, and while writing we are actually using these two properties. If you see this transaction app ID and transaction version, it will help to maintain that idempotent rights. So if you reprocess the stream, it will maintain this application ID and batch ID, and maintain the avoid this writing duplicate records. So how to link this flow, right? Like you have to create the flow and you have to create the sync. So using DLT declarative API append flow, we can create the flow and this link flow to target using the target name. So if you see here the sync name, which we used to create the sync, that way we can link append flow or read stream to the output sync. Similarly, we can create the Kafka sync. So DLT provides this create sync um, and the format, and then you can specify the options, Kafka options. And similarly, we can use to create the delta syncs as well. So instead of just Kafka, we can provide the delta sync. Also, it supports like a fan out, like it supports fan in. So let's say you are reading multiple sources and writing to the single target. We can use this append flow. We called it as a fan in option or fan in fashion. We can just write. So this will be useful when you are, let's say, you want to do backfill the data to the same table. So in the same pipeline, you can just add another append flow, and this whenever you require, like just backfill that data. So it will help to handle those kind of use cases. Uh, and then yeah, the last step, we can just run this cleanup steps to clean up these resources. So here I will conclude this demo. With that, I will wrap up today's. So today we walk through how we can use the prompt JSON in the DLT, how it offers the flexible way to automatically infer the schema and schema evaluation. After that, we saw the variant, how it simplified the JSON ingestion and make very fast reads. After that, we saw the event demuxing with common use cases and ways to handle. And then finally, we saw the DLT sync and flows API, how it making simplifying the demux processing. Uh, the resources what we used as part of this demo, they are available under this public GitHub repository. Both the demos are available. We can access. Yeah. Yeah, and thank you for your time. Let's see, I have open session for the question.